All right, today we're going to talk a little bit more about what an integral does to a function and what you can actually find with an integral. So let's begin. The integral of a rate of change is the total change. So this process known as FTC2 gives us the total change from time A to time B. For example, if V of t is the volume of water in a reservoir at time t, then its derivative V prime of t is the rate at which the water flows into the reservoir at time t. So an integral of V prime of t from time 1 to time 2 would give us the change in the amount of water in the reservoir between time t1 and t2. If the mass of a rod is measured from left to right, from the left endpoint, x is m of x. If the mass of the rod measured from the left endpoint to point x is m of x, then the linear density is p of x. So if you integrate the linear density from a to b, you get the mass of the segment from a to b. If c of x is the cost of producing x units of a product, then its derivative c prime of x is the marginal cost. And when you integrate marginal cost, you get total change in cost from some number of units to some other number of units. If the rate of growth in a population is dn over dt, then integrating dn dt from time 1 to time 2 gives you the total change in the population between those two times. If an object moves along a straight line with the position function f of t, then its velocity, when integrated, will give you the change in position, or the displacement. Remember, it's a little different than total distance traveled of the particle during the time period t1 to t2. Remember that displacement is the change in position from the start time to the end time, not the total distance traveled. It does not take into consideration any direction changes. So, a particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6, measured in meters per second. So to find the displacement from 1 to 4, we need to integrate. Anti-derive from 1 to 4. Anymore. Plug in your 4, subtract your 1 plugged in, and this ends up equaling, for lack of space, I'll go straight to the answer, negative 4.5, which means at 4 seconds, the particle is 4.5 meters left of where it was at 1 second. Now, total distance traveled is a little bit different. First, we have to take into consideration what happens between 1 and 4. Now, we set t squared minus t minus 6 equal to 0. We find that velocity is 0 at 3 and negative 2. Well, negative 2 doesn't matter, but 3 is in our window of time. And if we test, we find out that the particle is moving left at this section and positive at this section, which means to get total distance traveled, I'm going to write this symbolically, that's when it moves left. So that's still movement. We need to make it positive, so we put it in the absolute values, plus the integral from 3 to 4 of v of t dt. So work out both integrals, including this one, absolute value, the one on the left, and then add them, and you will get 10 and 1/6. On a calculator, you could do the integral from 1 to 4 if you have a calculator. If it's not a calculator portion, this option 1 is our only choice. But you could put absolute values around your v of t in the integral, and that would also give us the total distance traveled. A honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. So this is the starting value. This, when we integrate n prime of t, gives us total change in bees from 0 to 15, and I believe those are weeks. So overall, what does it represent? It represents, because that starting value is there, it's not just the total change, but it will give us the number of bees after 15 weeks. Without the 100 being added out front, we don't know where it started, and we can only say how much it changed in those 15 weeks. We don't know that it is the bee population. Use a graph to estimate the x-intercept of the curve, y equals 2x plus 3x to the fourth minus 2x to the sixth. Then use this information to estimate f(2). So, here's what this graph kind of looks like. So they want us to estimate the area of the region under the curve and above the x-axis. So we're estimating this portion here. And we find out that this intersects at 0, 0, because we're going to graph that and look for the zeros. And this is 1.37 something to 0. So, that is our curve, and we need the area. So the area would be the area from 0 to 1.37. Use more digits than that so that you are exact. Of our function, to remember how we find area, type it in your calculator or anti-drive and plug in those numbers, you get approximately 2.185 units squared, and I guess that's technically an approximate. So, if you need to hear it again, rewind, do whatever you need to, and we will talk about this more tomorrow.